Now example 2.34. Describe schematically the equipotential surfaces corresponding to A. Constant electric field in Z direction. So we know this thing, the equipotential surface is perpendicular to the electric field. So when your electric field that is in Z direction, it implies that as shown in the figure, your equipotential surfaces will be in XY plane. Then a field that uniformly increases in magnitude but remains in a constant, say Z direction. So if the direction of the electric field remains constant, Z, it implies that perpendicular to it XY planes will be there. So again, the equipotential surfaces will be exactly as shown in this above figure. Clear to all of you up to? Then for a single positive charge at the origin. So for a single positive charge, the equipotential surfaces will be concentric spherical surfaces as shown in the figure. Okay. Then D, a uniform grid consisting of long equally spaced parallel charged wires in a plane. So here suppose in this particular plane, the grid of the wires that is represented, this last one in the figure. So electric field that is perpendicular for these wires. So if we think about the equipotential surfaces, now equipotential surfaces are perpendicular to the electric field. It implies that in this particular case, the equipotential surfaces will be parallel to the plane of the charged wires. Clear? Now example 2.35. In a Van de Graaff type generator, a spherical metal shell is to be a 15 into 10 raised to 6 volt electrode. The dielectric strength of the gas surrounding the electrode is 5 into 10 raised to 7 volt per meter. What is the minimum radius of the spherical shell required? Okay. Now see here, the potential that is given to you 15 into 10 raised to 6 volt, and the electric field strength for the dielectric substance that is 5 into 10 raised to 7 volt per meter. Now see, here we have the equation for the potential at the surface of the spherical shell, that is V equal to KQ upon R. Similarly, we can write the equation for the electric field at the surface of metallic shell, that is E equal to KQ upon R square. Now rewrite this equation of electric field as KQ upon R into 1 upon R. But KQ upon R, that is V. So E that is equal to V by R. So R that is equal to V by E. Substitute the values of V, 15 into 10 raised to 6 upon value of E, that is 5 into 10 raised to 7, and solve it. You will get the radius of the spherical shell. Clear? Example 2.36. A small sphere of radius R1 and charge Q1 is enclosed by a spherical shell of radius R2 and charge Q2. Show that if Q1 is positive, charge will necessarily flow from the sphere to the shell. When the two are connected by a wire, no matter what the charge Q2 on the cell is. So in this case, first of all, we have to calculate the charge on each one. So say the radius of the inner shell, that is, or inner sphere, that is R1, and charge on it, that is Q1. So potential at the surface of the inner sphere due to its own charge, that is 1 upon 4 pi epsilon 0 Q1 by R. Now, potential at the surface of inner sphere due to outer shell. So for outer shell, whatever is the potential at its surface, that will remain constant up to the center. So we can say, due to that outer shell, the potential at the surface of the inner sphere, that is 1 upon 4 pi epsilon 0 Q2 upon R2. So we can write the resultant potential at the surface of inner sphere, that is 1 upon 4 pi epsilon 0 Q1 upon R1 plus Q2 upon R2, summation of these two. And now potential on the outer shell, that is 1 upon 4 pi epsilon 0 Q2 upon R2. Now if we take the difference of these two, then we will get the resultant potential difference. And here we can observe this thing, the potential at the surface of inner one, that is greater than that of the outer one. So if these two are connected by the conducting wire, the charge will flow from inner to outer. Clear to all of you? Example 2.37, answer the following. A. The top of the atmosphere is at about 400 kilovolt with respect to the surface of the earth, corresponding to an electric field that decreases with altitude. Near the surface of the earth, the field is about 100 volt per meter. Why then do we not get any electric shock when we step out of our house into the open? Because our body and the ground form an equipotential surface close to the surface of the earth. So we will never experience this type of shock. Now B. A man fixes outside his house one evening a 2-meter high insulating slab carrying on its top a large aluminium sheet of area 1 meter square. Will he get an electric shock if he touches the metal sheet next morning? Yes, because aluminium, that is a conducting one. So on aluminium sheet during daytime, due to discharging process, some charge will be accumulated. And when the person touch to the aluminium sheet, then through the body, the current will flow and charges will be grounded. And due to that, he will experience the shock. Then third one. See, the discharging current in the atmosphere due to the small conductivity of air is known to be 1800 ampere on an average over the globe. Why then does the atmosphere not discharge itself completely in due course and become electrically neutral? In other words, what keeps the atmosphere charged one? So the atmosphere is continuously being charged by thunderstorm and lightning all over the globe, and therefore it being charged one continuously. Then D. What are the forms of energy into which electrical energy of the atmosphere is dissipated during the lightning. So energy is dissipated in the form of heat, in the form of light, as well as in the form of sound energy. Clear to all of you?